All right, so a few times ago, we were looking at the concept of work and energy, the relationships between the two. And so I'm just going to reprise those concepts. The general equation for work, the net work is going to be comprised of the net force. It could be made up of one or more forces. F net cosine theta delta x. And we stated that you can only do work if the force and the displacement are in the same axis. Either they are, quote, working together. Here's delta x. And let's say that you have a net force in the same direction. In this case, they're parallel to each other. And that means that the angle between these two vectors is 0 degrees. And cosine of 0 is just 1. So it really just reduces down to F net delta x in that situation. It'll become F net delta x if theta is 0 degrees, as we mentioned. So cosine of 0 is just 1. So they're in the same axis. They can be anti-parallel or opposite directions, as in the case of friction. If the friction is the only force or the net force in the system causing the system to slow down, the object to slow down, or if friction is the dominating force, then obviously this object is going to have a slowing down effect. It's going to slow down due to friction. Say the object is moving to the right, but friction is moving to the left, whatever that force is. This is a situation where the force and the displacement are anti-parallel, opposites, and theta is 180 degrees. So those are the two conditions by which you can do work. Either x-axis the same way or the y-axis the same way. And we'll get into the y-axis when we deal with potential energy next week sometime. So just to kind of reprise what we've done several classes ago. All right. We mentioned that work can only be done if it's parallel, anti-parallel. Work cannot be done if the net force and displacements are perpendicular to each other. So I'll write up the word one time.
Mr. Kelly, can you go up a little bit?
Sure. So right here, is this fine?
Yeah. Yeah.
All right. So just to state while people are writing that, work cannot be done if F net and delta x are perpendicular. Can I move on?
Yeah.
Okay, so then in the symbol for perpendicular, as we know, the 90-degree symbol. And you know that from basic geometry, trigonometry, whatever, that cosine of 90 is 0, cosine of 270 is 0. So therefore, if we have a situation like we have a net force pointing this direction and the object is moving in this direction, well, then there's no work being done by this force. So therefore, because the angle between these two vectors is 90, cosine of 90 is 0, no work can be done. So this is a situation of no work. And same thing goes for if the angle is 270 degrees. It's basically it's the same thing. If, well, you know, as far as the unit circle goes, so if you have a force, so I'll continue with the red. Displacement here. So it's all 90, but in terms of rotating around the unit circle, that would be 270. And so the angle, cosine of 270 is 0, so no work can be done if your angle is 90 or 270. But it can be done if the angles are 0 and 180. Cosine of 180 is -1. Cosine of 0 is 1. So we can have some value. So just to summarize, come on. Okay. All right, 1 second. So again, work can be done if the angle between F net and delta x is theta equals 0 degrees or 180. Work cannot be done if the angle between F net and delta x is because it goes back to the equation for cosine theta. Cosine 0, 1, cosine 180, -1, cosine of 90, 0, cosine 270, 0. So that's really why, mathematically speaking, why you cannot have work at 90 and 270 and why you can have it at 0 or 180. So as long between these two vectors. Okay. So let's now go to back to our practice problems in a moment here. So does everybody have this? Anybody need to continue writing that? I'll hold off for a second here. So put the all of the work equations together, and then we'll come back to our sample problems. Okay, so we have the general equation for work. We also noted that net work, which is this, okay, just do, it's a matter of the order. You can put this all multiplication. F net delta x cosine theta, which is also equal to the change in kinetic energy. We derived last time the connection between work and change in kinetic energy, that when we have a net force, F net here, that causes an object to move from one position to another position, we are actually changing the speed of that object. So let's say the object was at rest when we moved an object to another position. Well, we changed its velocity from 0 to some final velocity. In effect, we altered its or changed its kinetic energy. So we know the basic equation for kinetic energy is 1/2 mass times velocity squared. So a change in kinetic energy would be 1/2 mass times final velocity squared minus initial velocity squared. So I have my box and it's sitting there at rest. Let's say the position is 0, everything's 0. And then I apply a net force to move it over to the right. And then I guess I'll just do the dotted box to indicate a new position. So let's say I have here x is equal to 0 and my initial velocity is 0. And at this point, I'll have x is something, like x final. So there's a displacement change and a speed change, right? So VF not 0, right? And so this box has mass. So in effect, I can use either of these two equations. If I have my net force and my displacement, I'm looking at a change of position. If I just have my mass and my two velocities, I'm looking at a change in kinetic energy. Well, they're all equal. They're all equal to each other. I can find work from either of these two situations. It just depends on what I have in the problem. So that is extension on the work equation. And so when we look at just the change in the speeds, we are looking at this one theorem that we denote as the work-kinetic energy theorem. That yes, work is equal to the F net delta X cosine theta, but in terms of the speeds, net work is equal to a change in kinetic energy, which is called the work-kinetic energy theorem. All right, so leave that there. And now I think we're ready for our sample questions. So just to remind you, we're on page 245, practice problems, and ebook, that would be page 84, I believe. So any questions on any of these things? This should be familiar, or if not, answer those questions. One last thing before the practice problems again. The units of work, energy are all joules, right? So we do our calculation and we report it as 2.5 joules, of work, if that's our answer. Right, so with that, I guess we can go on to our sample. And one question, oops. We are going to go to the catamaran problem. Okay, that is on page 245. So I'm starting with the catamaran. Okay, page 245, practice problems. We've seen this before. I want to do this again before we go on to the next one, which is, I don't know if we did the skater one. So have yourself ready. We're going to go to breakout rooms pretty soon. And I'd like you to do the 2 through 4, or actually 3 and 4. Okay, just to read. Yes.
Sorry, but what is the thing? What do the problems start with? Because we have different numbers.
The problem starts with a catamaran. If you can find that on page 245.
It's question 10 on our book.
Yeah, again, I didn't want to give the number out because it's different for me. All right, so page 245. A catamaran with a mass of 5.44 times 10 to the third kilograms. Can you find that?
Yeah, that's number 10, yeah.
All right, great. So this problem, we have a catamaran with a mass of 5.44 times 10 to the third kilograms is moving at 12 knots. How much work is required to increase the speed to 16 knots? 1 knot is 0.51 meters per second. So any problem we're solving, we're going to put down our known information, mass of the catamaran, type of boat, 5.44 times 10 to the third kilograms, initial velocity 12 knots, final velocity 16, and there's our conversion factor. You've seen those before, 1 kilometer, 1,000 meters, all that good stuff. So 1 knot is a half meter per second, 0.51 meters per second. And we're trying to figure out how much work it takes to change that speed. Remember, work is a change in kinetic energy as well as change of position under the influence of a net force. So those are all equal. So we're going to use the work energy part. Work is equal to delta KE, final, which delta means a final point minus an initial point. In this case, final kinetic energy minus initial kinetic energy equals 1/2 mass times final velocity squared minus initial velocity squared. So we have our initial and final velocities, but we need to convert them into meters per second because that's our common unit of velocity. So step 1, convert knots to meters per second. Now, of course, you're not going to do that for every problem. Every problem has its own dynamic. So just pay attention to what's going on. In this one, we're converting knots to meters per second. Initial velocity, okay, 12 knots. Well, we want meters per second, so we do 0.51 meters per second over 1 knot. Cross out the knots, and we get 6.12 meters per second. And our final speed, 16 knots, 0.51 meters per second over 1 knot. And that's roughly 8.16 meters per second. Now we have everything we need, put it into our work equation, and we got our work. Okay, net work, 1/2 mass velocity squared minus initial velocity squared, final velocity squared minus initial velocity squared. Plug in your numbers there, and we get 7.9 times 10 to the 4th joules of work needed to change the boat speed from 12 to 16. And if there was a decrease in speed, what kind of force is responsible for a decrease of speed or slowing down? Anybody remember that?
Friction.
Friction would be definitely Romero. Yes, friction would be the force to cause any object, boat, whatever, to slow down, because friction is always going to take energy out of a system. It's going to reduce the speed of an object. It's going to try to pull it from where it's going. It's always a negative influence on the object. Okay. And I was, talking about last time that the work-kinetic energy theorem is something like we're going to see in terms of impulse or momentum and impulse, or impulse is I. Again, you don't have to worry about what's in the parentheses, but it's very similar dynamics to that. Okay, so very good there. The skater problem. So I set it up for you, so make sure that you got the right answers, or if you got the wrong answer, we'll get them right now. So we have the 52 kilogram skater, moves at 2.5 meters per second and stops over a distance displacement of 24 meters. Let's say he goes from 0 to 24, displacement of 24. Find the skater's initial kinetic energy. How much of her kinetic energy is transformed into other forms of energy by friction as she stops? What is the work done by friction? And lastly, how much work must she do to speed up to 2.5 meters per second? Again. So the first case, what is her initial kinetic energy? 1/2 mass times initial velocity squared. That's all we need. $52 kilograms, and then her velocity of 2.5 meters per second squared. And you crank that out. Does anybody have that for me?
162.5 joules.
I couldn't quite hear that, so I don't know if it's your mic.
Okay. 162.5 joules.
Yes, 162.5 joules. Perfect. Thank you, Rita. I think that was you, right?
Yes, yes.
All right. Yeah, your mic is a little low. 162.5 joules. So that's our initial kinetic energy, and then we're going to figure out how much energy is transformed into other forms of energy by friction as she stops. So the work done by friction is just your change in kinetic energy. All right, which is, all right, so I'll write it out like this. KE final minus KE initial, which is also equal to 1/2 mass B final squared. It's V initial squared. So, okay, we put everything in there. We know that the final velocity is going to be 0, and so it's 1/2 of that. So it's basically the same thing, except that it's negative, right? Because we're going to, so 1/2 of 52, and then it's basically negative 2.5 squared, right? So it's going to be 2.5, with the whole thing negative. So we're going to put this in there and then leave that out. So it's the same thing, except that it's going to be negative 162.5 joules, which goes back to the case we were saying before, that friction is always taking energy out of a system. It's going to be negative, a negative result. So the work done by friction, negative 162.5 joules. And then it says, how much work must she do to speed up to 2.5 meters per second again? So if this is the amount of work to to slow down from 2.5 to 0, then the same amount of work is going to be to go from 0 to 2.5. because you're not changing the speed. I mean, you're not changing the amount. You know, you're changing the direction of it, but you're not changing the amount. So the work will be the same. So for part C, it's the same amount of work. So just to see it, I mean, because the question is simply put, how much work does she need to get back up to that speed? So she's starting from 0 to go back to 2.5, which is now final. It's the same amount. Her mass didn't change. It's not a different person. So 1/2 of 52, you know, final velocity squared minus initial velocity squared. 1/2 52. So she's going back up to 2.5 from 0. So she came from 2.5 to 0. Now she's going back to 2.5 from 0. So we're just changing our perspective on it. So 0 squared. So that's that. It's the same amount. Any questions on that one? Let me see how that works together. So, because we're going to have some homework questions on this and power. So make sure that we can get the dynamics of that. Okay, so question 3 for me, the one with the car, the 875 kilogram car. So and it goes from 22 to 44. What are the initial and final kinetic energies of the car? How much work is done on the car to increase the speed? So this was pretty standard. If you know are following the concept work and kinetic energy. So we're just going to do it one by one. Get the initial kinetic energy. And then that's 22 squared. Crank that through, and that's your initial. Do these simultaneously, and we'll come back. Same formula for final. So I'm going to do 1/2 875 times 44 squared. All right, so let's do those. So hopefully you get 211,750. I like scientific notation because these numbers can get large. So that's going to be 2.1 times 10 to the 5th joules. And likewise, this will be 8.47 times 10 to the 5th. So everything being equal, we're doubling the speed. The kinetic energy goes up by 4 times, roughly. So we have that squared in there. Else it would be double, because it's 22 and 44. You can see that just by the numbers. Questions on that? Finding the initial and final kinetic energies. And the work is just going to be the change in between the two. So we know from our principles that total work in terms of energy is change in kinetic energy, which is final kinetic energy minus initial kinetic energy. Well, we just subtract the two numbers. So it's all fits. You can all put it together as such. So 8.47 minus 2.1, and I have the understood 10 to the fifth as a common exponent, and it's going to be 6.3. Yeah. Okay, 6.37 times 10 to the fifth power joules. That's your work. That's the work required to done on the car to increase its speed. All right. Everyone all right with that? Work is the change in kinetic energy. So let's end off our day by talking about this concept of power. Let's see if we can summarize, make things simple. Power is basically the rate at which you use energy. We've talked about changing energy and displacing the object and under the influence power of a net force. Well, power, in a sense, is the rate of time. Anytime you see rates, time interval, the rate at which you use energy. How much time does it take you to change your kinetic energy? How much time does it take you to change your potential energy? The rate at which you use energy. And more specifically, let me be a little bit more specific with that. So rate at which you change your energy. The same difference, the semantics, but I want to be a little bit more specific there. The rate at which you change your energy. So you're walking, you're running track, you're going to change your energy from one value to the next as you're running, expending a lot of energy to increase your speed. So the time interval is the rate at which you change your energy. So basically, power is delta E divided by time. And this is energy over time, delta E over T. And we know that the change in energy is also known as work. So that's a common equation for power. Power is work divided by time, or change in energy divided by time, because work is a change in energy. And the energy can be of two forms. We're going to see the other form next week, but this form we've seen this week is kinetic energy. Work is equal to a change in kinetic energy, and also potential energy later on. So we're going to just glob it together and say energy. The rate at which you change your energy is power. And so its units are watts after James Watt, 18th century, doing a lot of work in power.
Mr. Kelly,
Yes, sir.
can you go up a little bit?
Right here. Where do you need?
Can you go a little bit down, just a little bit down? Yeah.
Yep. Okay. So the units of power are watts. You have heard of those. You see your light bulbs all the time with the W, 75 W, 60 W, watts, the units of power. And also, depending on the time interval it takes you to use your energy is going to correspond in how much power you have expended, you have produced. So let's say that, you know, an example out of the book is that if we have two forklifts that's going to, they're going to have the same change in energy, but one of them lifts, if one of them lifts a load in say 2 seconds, and the second forklift lifts the same load in like 10 seconds, well, then the one in 2 seconds is going to expend more power. Why do you know that for sure? Because this is an inverse relationship. If the amount of time it takes you to perform work is reduced, your power increases. Whereas in the other case, if the time it takes you to produce work is large, your power is small. So you want to be very powerful. That means if you're lifting weights like this, you're very powerful. If you're just, you know, just lifting them up, you know, like that, you're not as powerful, weak or whatever. But you need to, you know, build up to that, you know, lifting up in a small amount of time. So that's just an example of power in real life. Okay. If it takes you less time to do some work, you're very powerful. More time, more powerful, less powerful. Okay. So inverse. Okay, so now what I want to do is just finish things off here with another expression for power. So we have seen power is work divided by time, which is, you know, same thing as change in energy divided by time. We also know that work, or network, if you will, is force times displacement, which we'll just commonly just call delta x over t, because we know from our first equation that this work is equal to F delta x over delta t, if you know, if we make, because it is a time interval. So technically this is all takes amount of time. It's not just instantaneous. It's, you know, it is a time period, to do something, to change your energy. So work is F delta x over delta t. Does anybody remember the equation for delta x over delta t? Can I re-express this somehow? Starts with a V, as in Victor.
Velocity?
Yes, it is. Delta x over delta t is my velocity. So power can be expressed in all of these forms, including force times velocity. And this is a constant velocity, okay? There is no change in the velocity because by definition, V, average velocity, if you will, change, constant. Velocity is delta x over delta t. So if you have an object under the influence of a force, under a constant speed, you are producing power, okay? So which is equivalent to all these different forms. Power is work over delta t, energy delta t, force times velocity. It just depends on what you have in your problem to choose from 3 different ways of finding power. Okay, so work over delta t, which is change in energy over delta t, which is also equal to force times velocity. And again, whoops. And again, your power is watts. So That's kind of it on the power introduction there. We'll continue next time, but so one thing I wanted to do is one example, and we'll be done for our day. So if we're going to scroll down in our text, in your textbook, it's page 246, same page 84. And we're looking at the practice problem where we have a cable attached to a motor. It lifts a 575 Newton box up a distance of 20 meters. The box moves with a constant velocity and the job is done in 10 seconds. What power is developed by the motor in watts and kilowatts? Okay, so when newtons is used to describe an object, that's its weight. Fg, that's how much the box weighs. Because it's an adjective in this case. Let's say 575 Newton box weight. Distance is 20. So we have a force, and the implication is going to be moving with a constant velocity. So it's very useful for us to use force times velocity equation that we just derived there. So it's going to be lifted up 575 newtons the other way by force of gravity, and it's going to be lifted a distance 20 meters in 10 seconds. So we can get the velocity by displacement divided by time. We have the force already. So let's put that together. We have 575 newtons. Velocity is, remember, velocity is delta x over delta t. So we can use a delta x here. And we have it. So that's just 2. And 1,050. 1150. Carry the 1. Okay, so that's going to be 1,150 watts of power produced, developed. And they wanted to express it in kilowatts. Well, much like the kilometer is 1,000 meters for a kilometer, 1 kilowatt is 1,000 watts. So if we want to take this and express it into kilowatts, how many kilowatts would that be? Anyone? Just divide by 1,000.
$1.15 kilowatts.
Exactly. Exactly, Joshua. Sure. If anybody did not see that, 1,150 watts, we know that there are 1,000 watts to 1 kilowatt. So watts goes away, and we can just divide by that to get what Josh told us, which is 1.15 kilowatts of power. And that's just opening statement on power. We'll continue that next time. So keep these notes. Don't turn them in. Keep them for next time. I will be giving you a couple of questions for next week. So review your notes, review your text, and we'll come back and talk more on this.
We turn in the notes.
We do not turn in the notes.
Like you're not gonna post something so